Okay, so we're going to talk about radiation protection and radiation biology, and you have several objectives that you'll need to be able to answer. This subject is just scraping the surface of what you need to know. You're going to have a couple additional courses just in these topics to ensure that you really know them well for your national exam. So when we're looking at radiation as an ionizing energy, when we talk about radiation, we're talking about how electrons can knock other electrons out of atoms. So it's radiation that has significant energy to cause the ejection of electrons from atoms. So the loss of electron results in ionization. Ionization can have biological effects that we're going to talk about a little bit. So the benefits must outweigh the risks of any diagnostic X-ray study like we talked about in the prior lecture. So there's two sources of ionizing radiation. There's natural, which is found just in our atmosphere that we're exposed to every day. Within our biology and our metabolism, we produce radiation also. There's radiation in bananas and potassium. There's also man-made radiation, and that's really what we're going to be talking about. As our bodies are exposed to natural radiation all the time, our bodies are not exposed to man-made radiation, and that's the focus here. So human-made radiation comes from several sources. We have medical and dental exams are the largest portion of radiation exposure. So we have talked about this in the past, but the conditions necessary for X-ray production, you have to have a source of electrons. You have to have a means for setting them into high motion, and you need a way to suddenly stop them or decelerate them abruptly. So your source of electrons that comes from the cathode. So when we dial up our MA, we're setting how many electrons we are going to have boil off of the cathode. We need a way to put them in high-speed motion, and that's with our KVP. We use the potential difference there. So when we apply the KVP, it shoots them across the tube, and they hit the target, which is their source of sudden deceleration. So that's when the energy is transformed into a photon. So your X-ray tube design. The X-ray is a diode tube, so it's glass envelope, and we talked about how it's Pyrex, and because it can handle high heat. And the X-ray beam is produced is heterogeneous, so you have a lot of different energies within your beam. So if you dial up 70 kVp, you're going to have anything from basically 0 all the way up into 70. You will not have more than 70 because that's the maximum that you'll have, but you're going to have a huge spectrum of different energies within your beam. So it's not homogeneous, it's heterogeneous. The X-ray beam is expressed in kilo-electron volts, so keV. So the X-ray beam leaving the tube towards the patient is called your primary beam. After it goes through the patient, then it's called your remnant beam. So your X-ray beam can undergo 3 possible paths when it hits matter. So when it hits the matter, it can be totally absorbed, or it can pass through with no loss of energy, so it goes straight through the matter, or it undergoes scattering and secondary interactions with some loss of energy. We're going to talk about those a little bit. So X-rays interactions with matter, we have coherent or classic coherent scattering. I just call it coherent. You'll hear other instructors just call it classical. So you're going to hear different things, which makes life fun, right? You'll hear Thompson also. So that also is another name. We do deal with coherent scattering mainly with mammography. There is some coherent scattering within our X-ray tube, but we usually use filters to filter it out. It's really low. There's photoelectric interactions where the photon is completely absorbed within the matter. We have Compton, where the photon comes in and scatters into a new direction, and so the Compton scattering is really what the occupational dose is. There's pair production and photodisintegration. Those two are usually found in radiation therapy. So those are the two really high energy ones. We're going to talk about each one a little bit. So with classic coherent scattering, also Thomson, Rayleigh, there's different names you're going to hear for it. Jeremy and other instructors are going to call it different things, which, like I said, don't be surprised. It's called classic coherent scattering. I just call it coherent. So involves very low energy X-rays. It's below 10 keV. The X-ray interacts with the whole atom. The atom becomes excited and emits X-ray with the same energy as the incoming. No ionization happens, no energy transfer to the patient or matter. So as you can see here, the wavelength here is the same as the wavelength coming out. So it hits the atom, gets it so it starts vibrating, and has it turn the corner. So there's no ionization really within the atom. So it excites it, which is not good, but we consider scatter any time that a photon changes direction. So this is coming in and it's turning the corner, so it's changed direction, therefore it's considered scatter. Okay? Photoelectric, this is a little more complex. Well, I shouldn't say a little, it's a lot more complex. It occurs within the diagnostic range, so this is really predominant. The photoelectric and the Compton are the two that give us our image. So photoelectric effect occurs in diagnostic range. The incoming X-ray photon is completely absorbed by collision with an inner shell electron. It's usually K or L that it's crashing into. The photoelectric interactions contribute greatly to the patient dose. So the reason why this is the highest dose to the patient is that it's completely absorbed within the matter. So it's completely absorbed by the patient. So the electron or photoelectron leaves the atom, creating an ion pair. The free electron eventually unites with other matter. The secondary radiations creates as a result of electron cascade from the outer shells to inner shells. So here we have your incoming photon. It hits an inner shell electron. You get a photoelectron that comes out, and then you have this vacancy in the K or L shell. Well, that makes the atom very, very unstable. The inner shells need to be filled. So when it drops down from one level shell to another, so this is L to K, what happens is it gives off what's called a characteristic photon. So that characteristic scatter X-ray is additional exposure. So it does it for each level as it drops down to fill those inner shells. All right. They call that characteristic cascade. All right, so Compton. Compton scattering occurs within diagnostic ranges, though the incoming photon collides with an outer shell, where photoelectric is inner shell, but Compton is outer shell electron, creating a free Compton electron, which we call recoil, and an ion pair. So here it comes in, here's your incident, here's your wavelength. You can see your wavelength coming in, hits an outer shell electron, knocks it out, and it's called a recoil electron. So then you have the difference between here and here, the angle of scatter, and a decreased photon energy here. So the incoming, if you found this angle, you'd be able to, if you added these two together, their energies, it'd be the same as the incident. So the incident comes in, knocks it out, and you get a recoil electron, and then you have your scatter. So the nature of Compton interaction contributes significantly to occupational dose. So this is what we're being exposed to as occupational workers in the field. So the incoming photon loses some of its energy through collision, scatters off a random direction or angle, so it hits, gets bounced off in another angle, and undergoes an interaction until the energy is gone. So it's going to keep interacting until it is absorbed by photoelectric, or keeps having Compton until it leaves the body, and whether it hits the occupational worker or it hits the image receptor. So it can make it out of the body or the matter depending on the energy level. So if you're dealing with a really high kVp, a really high energy photon, the likelihood that it's going to be able to interact multiple times through Compton, or if it's a lower energy, it can interact multiple times and then eventually be absorbed through photoelectric. Okay, so pair production. It's very high keV. So actually it's in MeV, which is mega electron volts of energy. So in order for pair production to take place, you have to have 1.02 MeV of energy. So it interacts with the nuclear force field around the nucleus. So it comes in really high energy. See how tight this is? And it interacts with the force field of the nucleus. And what happens is that it pops out a positron and a negatron. So you can see the two here. So the positron interacts with the free electron and it goes through what's called annihilation reaction. And with that, it explodes again and you get a 0.51 MeV photon going in two opposite directions. So the 0.51 and 0.51 add up to the 1.02 MeV of energy. So there you go. Pair production. So two particles reappear, each with equal, oh, this is still under pair production, I'm sorry. So the two interact and you get a 0.51 MeV and a 0.51 MeV. So the positron collides with the free electron and creates an annihilation reaction. The annihilation reaction creates two photons at opposite angles to each other. So when you think of pair, think of 0.51, 0.51 equal 1.02. So that's your pair production at radiation therapy levels, MeV. Okay, photodisintegration. So requires a photon energies that are extremely high. Incoming photon interacts with the nucleus of an atom, creating nuclear instability. So this is also radiation therapy levels. It comes in and you get a nuclear fragment out. Not good. So a nuclear fragment is given off by the nucleus and seeks stability. So common interactions in the nuclear industry. Now let's go into our units of measurement. So the SI unit, which is the International System of Units, was adopted in 1985, and it actually just changed to where you guys now will have your national exam on the SI units, not traditional units. So what's displayed here is the Roentgen, the Rad, the Rem, and the Curie. Those are all being changed over to the SI units. So it talks about coulombs per kilogram, but we actually call it air Kerma. So the Roentgen now is the air Kerma. We have the gray, and we have the gray with the lowercase a and the gray with the lowercase t. The A is for ionizations in air, which can be measured as the Roentgen, or the gray with the lowercase t can be the absorbed dose within the tissue, T tissue. So the radiation equivalent man, which is the REM, is actually now the sievert, and that's how all of our radiation badges are read in sieverts. And then the Curie is now with becquerel. So easy to remember that Marie and Marie Curie were with becquerel when they got the Nobel Prize in physics. So easy to remember that way. So the Roentgen measures exposure in air, is not used to express absorbed dose to individuals. It's a measure of ionization in air as a result of exposure to X-rays or gamma rays. It's being phased out as a unit of measure since exposure may be expressed directly as coulombs per kilogram. So the RAD, so is radiation absorbed dose, measures the amount of energy absorbed in any medium, defined as 100 ergs of energy absorbed in 1 gram of absorbing material. So the RAD has been replaced by the gray in the SI system. So 1 gray equals 100 RADs. The REM, which is the radiation equivalent man, is a unit of dose equivalence. So it counts for the different types of radiation and their biological effects. So all of our badges are read in now what's called the sievert. So the REM has been replaced by the sievert. You'll still notice that Instadose still talks about the REM, and your badges, I should still say the REM. They need to be changed. So I've actually put a call into them to have the radiation badges read out in sieverts. So it's a process. So 1 sievert equals 100 rem, expressed as the product of the absorbed dose in rad and a radiation quality factor. So the rad times the quality factor is the rem. The Curie is the measurement of activity of a radioactivity material or radionuclei used in nuclear medicine and radiation therapy. The Curie is the unit of activity equivalent to 3.7 times 10 disintegrations per second. So now we're using the SI unit of activity is the becquerel. It's defined as 1 disintegration per second. It's a little easier. So it is 3.7 times 10 becquerels is 1 Curie. That's not easy to remember. Okay, so standard of exposure. So they're regulated by the FDA and its Center for Devices and Radiologic Health. Effective dose limits have been set to minimize the biological risks to exposed persons. An individual's dose should be kept as low as reasonably achievable, so Lara concept. The whole body effective dose for occupational workers is 50 millisieverts or 5 rem. So the whole body dose equivalent for the general public is 1/10 of the occupational workers' annual dose. So dose response relationship. So when we talk about response curves, this is one of your first ones that you're going to be seeing. So physicians use a risk versus benefit rationale when ordering ionizing studies. Benefits of exams must outweigh the potential risk from exposure. So dose should be kept as low as possible, and a no dose is considered totally permissible. So within radiology, we have what's called a non-threshold dose. So you can see it starts from 0. So this is your dose and this is your amount of dose. So if this is 0 right here at the corner, this is called a no threshold dose. So any dose to radiation can cause biological effects. So this is called a non-threshold dose. If there is a threshold, then we'd call this a threshold dose. So radiation is a non-threshold dose. All right. Biological effects of radiation when we talk about the cell. So let's go into what happens. So with cell biology, cells have 2 major parts. There's the nucleus and the cytoplasm. Within the cytoplasm, cell organelles are suspended in the cytoplasm. So genetic material of the cell contained with the nucleus is chromosomes, genes, DNA. 80% of a cell is water, and 2 classes of human cell is somatic, so it performs body functions, and genetic, which is reproductive. So I broke it down very, very simple. This is not nearly everything you need to know, but you've had courses in this prior, so we're going to go right through it. So the radiation of cells. There are 2 theories of cellular irradiation damage exist. So cells have different degrees of radiosensitivity. Cellular radiosensitivity is a principal result of the rate and duration of cellular mitosis. So I'm going to start down below here with the direct hit theory. It involves X-ray photons hitting an important macromolecule such as the DNA, causing genetic damage. In an indirect theory, involves the irradiation of water, which is 80% of our bodies, right, or the cell. And so irradiation of water molecules in a cell cytoplasm and creates free radicals. Those free radicals cause damage to the cell and cell death or changes within the cell. So cellular response to radiation results in radiation to a cell. It can die, it can delay mitosis, or it can alter the mitotic rate. So functions of cell survival to radiation, it depends on the cell's radiosensitivity, the type of damage, the type of radiation, the radiation exposure rate. Are we doing it every day, or do you just get one big huge blast of radiation, and the total dose of radiation given? So did you give 10 treatments given and fractionated, or did you give one big dose? So the radiation exposure rate along with the total dose of radiation given, if we do it over 2 days instead of 10 days, the dose is going to be a lot higher, and you're going to have a lot more biological effects if you do it in 2 days rather than 10 days. So all that comes into play. Most cells can recover from radiation damage, which is really, really good. That's why we do fractionated doses when we're doing radiation therapies, because healthy tissues can recover, which is great. So total body's response. Acute radiation syndrome is not good. So it requires large amounts of total body exposure. There are early effects and late effects. So the early effects, you have the prodromal stage, which is nausea, vomiting, and diarrhea. You have the latent stage where the organism, you feel good, but there's biological changes happening, and in the manifested stage, you're going to feel them. So the organism feels the full effects of the exposure. You either recover or you die. So it's one of the two. There's late effects, so you have somatic effects, so developed in those exposed, so it's going to affect how your body's working. You have genetic effects. It develops in future generations. You won't see it in your generation, but you'll see it in your offspring. So, radiation syndromes. Oosh. These doses are far greater than those received by us as workers and by patients. There's bone marrow syndrome, which is 2 to 10 gray. So you have 6 to 8 week mean survival or recovery. So in 6 to 8 weeks, you're either going to recover or you're going to die from bone marrow from 2 to 10 grays. Gastrointestinal syndrome, so 10 to 50 grays. You have a 3 to 10, I didn't put down 3 to 10 day mean survival. So you are dependent on if you had 10 grays, you're probably going to go for a longer period than you will 50 grays. 50 grays, you probably have about 3 days before you die. Yikes. So the central nervous syndrome, it's above 50 grays. So if you receive that amount, you are going to die in 2 to 3 days. So pretty much nothing we can do. Even with gastrointestinal, keeping you hydrated and trying to keep you alive, we usually fail. All right, so protecting the patient. The cardinal rules for protection: time, distance, shielding. So you always want to minimize the amount of time around radiation. Your distance, you want to maximize your distance from radiation wherever it is practical to do so. So you're going to do this for the patient and for yourself. Shielding, use lead aprons and gloves for the patient and yourself. X-ray beam restriction, aka collimation, so that protects the patient and protects you from the scatter. And your image receptor speed, so the faster the speed, the more sensitive it is to radiation, which means the less radiation you need to use, which means less scatter. If you use filtration, it filters out lower energy photons, which takes out that classical coherent scattering, which is really nice. Optimal exposure techniques. So with CR and DR, we really take our KVP up high and drop our mass. Mass is dose. Mass is directly related to dose. So you want to take your mass and you want to drop it down and you want to raise your KVP as much as you can. So protecting yourself, same thing, time, distance, shielding. So you're going to do the same thing as you would for the patient. You're going to do it for yourself. We're looking at the inverse square law also on calculating your dose, so take a look at that in your book, be able to calculate it. It's important that you understand that as you double your distance, what it does to your dose. Your dose drops by 4, so it's great. Shielding, you should always have lead shielding on. You should wear gloves, leaded gloves when you're working in the exposed field, and you always are to have your personal monitors on. All right, radiation monitoring. So any occupational worker who is regularly exposed to ionizing radiation must be monitored to determine the exposure. Any worker who is likely to receive more than 1/10 of the recommended dose equivalent limit should be monitored. So it's known as personal monitoring dosimeters. So common monitoring technologies, there's the optically stimulated luminescent dosimeter, so the OSL, there's the film badge, there's the thermo-inescent dosimeter, so the TDL, and the pocket dosimeter. Know what each one does. So the occupational personnel monitoring monitors measure the quantity of radiation received on the basis of conditions in which the radiographer was placed. Exposure data are collected for a specific period of time. These are usually good for 30 days and you have to send them back in. So occupational monitoring continued, you need to wear it at your collar level, you wear it outside your lead apron, devices should face forward, pregnant workers need to have a second device worn at the waist level under the lead apron. All right, in conclusion, radiation has the potential to create ionization in human tissue. Ionizations can be harmful and cause cell disturbances and genetic alterations. Effects may be early or late and are dose dependent. Use of cardinal rules for protection. So you need to use the time distance shielding for yourself and the patient. Radiographers should have a professional responsibility to consistently practice ALARA. All right, so that's just scraping the surface on your basic radiation protection and biology. Be sure to read your chapter and review this PowerPoint to do well on your quiz.